Yes. Yeah, yeah, for sure. Yeah, that's fine. Yeah, just like, you know, yeah. Oh, there we go. Yep. Yeah, it's gonna be recorded too. It's gonna be recorded too. It'll be posted and it'll be recorded. So there'll be, yeah. Okay. Oh. Can you hear me okay at the back? Yeah. Cool. Okay, so we're gonna get started here, as the last few people trickle in. So to begin, I guess I'll introduce myself. I'm William Hamilton, and this is the first lecture of Comp 551. This is Applied Machine Learning. And I think one important thing for everyone to know at the beginning is that the slides will be posted and the lectures will be recorded. So you don't need to stress about taking notes, and you can know that you can watch the lectures offline. I know it's a pretty big course. It's actually the biggest 500 level course in McGill CS history, so it might get a little cramped in here, but you can always watch the lectures offline afterwards. And so for today, going to be pretty light, just going to go over the syllabus, give a quick summary of the course content, a broad introduction to machine learning, and also discuss some example machine learning applications. So this is really just to set the stage, give a bit of the vocabulary, the expectations for the course, before we dive into the material on Thursday. So at a high level, just starting with the objectives for this course. So this is an applied machine learning course, but really the goal is to have everyone here develop a rigorous understanding of the statistical foundations of machine learning, as well as the software tools, and most importantly, best practices. So it's applied machine learning, but that doesn't mean we're just going to be using off-the-shelf toolboxes all the time. We're going to learn about the fundamentals. There's going to be a reasonable amount of math involved, and again, really a big emphasis is going to be on best practices, both in terms of how we design machine learning algorithms, but also very importantly in how we evaluate them and how you can read, say, current machine learning literature with maybe a bit more critical eye. So just very quickly, a little bit about me. So I am a new assistant professor here at McGill. I actually did my bachelor's and my master's here at McGill And I took this course in its first year, I think 7 years ago. I then left. I was at Stanford for the last 5 years, and now I'm starting here. And in addition to being an assistant professor here at McGill, I'm also one of the core professors, core members of the Mila AI Institute of Quebec. So this is a new initiative. We have a nice new building, so there's a large group of not just me, there's about 15 other core machine learning faculty here at McGill as well as at University of Montreal. So it's a really exciting time for AI and ML here, and I think that's evidenced by the fact that this course has grown about 5 times in size since when I took it 6 years ago. So, okay. And then in terms of the kind of research that I do, obviously I work on machine learning, but the core part of my research isn't just machine learning, it's actually working at the intersection of machine learning, network science, so social networks or biological information networks, and natural language processing. And I put a big emphasis on actually using machine learning to understand complex systems. So actually trying to use machine learning to enable different kinds of social and biological science applications. And a lot of what this involves is machine learning with either graph-structured or network-structured data. So this isn't going to be the focus of this course. I'm hoping to get into this towards the advanced lectures side later in the semester. But in my research, really what I'm focused on is how can we work with things like social networks or biomedical networks or networks of neurons in the brain and build new kinds of machine learning methods that can work with this kind of data. And this is a relatively new area, but it's the development of a bunch of techniques that are often called graph neural networks or graph convolutional networks. And if people are interested in this, feel free to reach out to me. I have a lot of tutorial materials that I'm happy to share. And of course, since this is a course not just on machine learning, but on applied machine learning, just quickly highlight a couple of the sorts of applied works that I do. So again, my core application focus is on one side on computational biology, and on the other is computational social science. So on the computational biology side, a lot of my work involves trying to figure out what are new ways that we can use existing drugs to, say, treat diseases that they've never been tried to treat before. So trying to predict new interactions between drugs and diseases or new side effects of drugs. So that's on the computational bio side. A bit more on the computational social science. I'm presuming that a fair number of you are familiar with the Pinterest website where you can go and pin content you want to save for later. And actually, some components, I can't say exactly what parts of it, but some components of how Pinterest actually recommends you pins is actually based off my PhD thesis from Stanford. So that's the kind of research, applied research that I do. And these are topics I'll hopefully get to touch on in the last few lectures of the semester. But of course, with a course of currently 365 students, I am not alone. So at the moment, there are 9 TAs, but likely moving up to 11, led by the head TA, Joey, and he's a really good point of contact. I receive a lot of email. I try my best to reply to everybody, but if you're getting stonewalled, you need a really quick answer, Joey's a very good person to reach out to. Please put Comp 551 in the subject line. It really helps for us replying to things. And the TA office hours will be set in the next week or so. We're hoping to have 10 hours of office hours a week at minimum, hopefully a bit more than that. So hoping to have enough office hours to answer everybody's questions. So what about the actual content of this course? So in terms of topics, this is a laundry list of everything we are ideally going to cover in this course. I'm not going to go over all of this in painstaking detail right now, but the key point is that we're going to start with really basic machine learning methods, really the fundamentals of machine learning, which is linear classification and linear regression. We're going to have a lot of emphasis on how you actually evaluate and what it means to have models that are, say, overfitting or generalizing, and these key principles that are going to matter throughout all the machine learning that you do. And then following on that, we're going to introduce kind of increasingly complex models, things like naive Bayes, support vector machines. And then in the second third of the course, there's going to be a big focus on deep learning methods. So I know a lot of people, a lot of interest in learning about deep neural networks, things like convolutional networks or recurrent neural networks, and this is going to be a major unit that's coming just around the March break. And so in terms of structure, of course, in class, there's an expectation that people do attend the weekly lectures. Of course, you can watch them online. Again, I understand it's a huge course. It's a big room. There's a lot of people, so I understand if you want to watch things outside of course as well, but I do recommend you come. It's very good to ask questions. And with that, I will say, please feel free to interrupt me at any point if you do have a question today about the structure or the content. And then in terms of outside of class, so there's going to be 3 optional tutorial sessions. So starting next week, I'll give a bit more information on that, just an introduction to Python. These are going to be tutorials to help you learn about some of the toolkits that are quite standard in machine learning, things like scikit-learn and, say, PyTorch for deep learning. And then in terms of homework and the work you're going to do outside the course is going to be projects, online quizzes, and I'll go into a bit more detail in this in just a few minutes. But a key thing to note here is that there's really 2 complementary aspects of this course. So on the one side, there's lectures, and this is where you're going to learn a lot of the statistical nitty-gritty details. There's going to be a quizzes and a midterm evaluating your knowledge of these details. And then there's also going to be these projects, which are complemented by the tutorials, and this is much more hands-on experience. So of course, in a lecture, I can't actually give you hands-on experience, so it's important that you really put time and effort into these projects, and highly recommend that you do attend the tutorials as well. And in terms of requirements, I know this is all on the webpage, but it bears reiterating. So there's going to be an expectation that everybody here is competent and skilled at programming. It's okay if you've never programmed in Python before, but there's going to be a bit of a rough ramp up then in the first couple of weeks because everything is going to be in Python. So if you haven't used Python before, that's okay, as long as you have experience programming ideally in more than one programming language. And again, we're going to have a tutorial to get people up to speed on Python. You also really should have taken Math 323 or something equivalent. It's really important to have a foundation in probability and statistics. Otherwise, the quizzes and the midterm are going to be really hard. Also, related to that, calculus and linear algebra, obviously. I'm assuming if you're in computer science, which not everybody here is, you will have taken courses like, say, Math 124 and also the introductory calc courses. You should be confident in your ability to do calculus and linear algebra. That's going to be a big part of really the entire course. And it's recommended that you, say, take in 424 or have an interest in some knowledge about AI, but that's definitely not required. And then finally, this shouldn't be relevant anymore, but if you took Comp 652, which is the machine learning course, not the applied machine learning course, before 2014, you cannot take this course. So again, that probably is almost outdated now to have on here, but just in case. And it's okay to take this course and then take 424. So that is technically all right. And just to reiterate, for those of you who are concerned about your Python skills or just want a quick refresher, there will be tutorials next week. So they're going to be Tuesday and Thursday evening, 5 to 7 p.m. in Adams Auditorium. And I'll have more links. There's in my courses. These slides will all be up, and there's a course website, so all these links will all be there. So you don't need to write this down frantically. Okay, so probably the thing that's perhaps the most important in terms of syllabus-like material. Yep. Yes, I should say there will always be 2 versions of the tutorials. They're just the exact same tutorial twice, because I know people might be busy. So yeah, it's just the exact same tutorial twice. Okay, so in terms of evaluation and expectations, so the big breakdown here is 10% of your grade is going to be weekly quizzes. I'll explain those. 60% is going to be these projects/assignments, and then there's going to be a midterm towards the end of the semester, and that's worth 30% of your grade. So really the big weight towards these applied projects. So how do the quizzes work? Quizzes going to be on my courses. They're online quizzes. There's going to be 2 every week, 1 on Tuesday, Wednesday, 1 available Tuesday, Wednesday, 1 available Thursday, Friday. we just take your best grade out of those 2. You have an hour once you start. There's only 5 questions. And again, only your best grade from the week will count. And these quizzes are not supposed to trip you up. They're really supposed to just checkpoint your understanding, make sure you're staying engaged with the course, and also give you practice for the midterm. So there will be a quiz 0 next week, not worth any grades. It'll be kind of a self-assessment thing. It'll be a little tricky, but the idea is that if you really struggle with it, it maybe is time to reevaluate whether or not you should maybe wait a semester before coming back to this course. There'll be a midterm, like I said. Only thing to know right now is it's going to be the evening of March 26th. And if you really know you're going to be out of town then, better to just let us know ASAP so we can get a sense of if we need to make alternative arrangements. But there'll be a lot more detail in the midterm later on. We'll give you a practice midterm and so on. And then most importantly, the projects. We'll introduce each of these as they come, but there will be 3 mini projects. 2 of them will involve competitions where your grade's somewhat dependent on how well your machine learning model performs. And then there'll be a final project where you actually have to find a recent machine learning paper and reproduce some of the results in that paper. And there'll be a lot more detail on this as the course progresses, but some important things to know right now is they're all going to be group projects. So why group projects? Well, for one, this being an applied machine learning course, it's important that everybody gets experience doing machine learning in the way it actually works in the real world, and that involves working on teams. So there's a very good experience for you. We're going to ask that people rotate their team so you don't use the same team all semester. That's to make sure that there's not one student who's doing all the work for 2 other people the whole semester. And generally, everybody in a team is going to get the same grade. So we're going to ask people to say what they contributed, but the expectation is you're all working together. These are group projects. There's 365 of you, so there's a lot of groups, and it's important that people all contribute within their groups. And again, there'll be a lot more information on this as the semester progresses, but just important to keep in mind that if you really want to do the final project with your best friends, you might not want to do the early projects with them because, again, you're expected to change at least one member of your group every time. So not too exciting, but readings, everything's going to be in the lecture slides. There's no required readings, really. There's a required reading just for kind of fun today, but there's no mandatory textbook. There's a whole bunch of great material online. There's some links to these textbooks on the course website that I'll show in just a second. Also, beyond these textbooks, in this day and age, you can find really great tutorials on YouTube all over the place. Like I said, the core stuff you're going to be evaluated on is all going to be in the lecture slides. But if you feel like you want kind of a second telling of some of the content in this course, these textbooks are great, as are tons of different online resources that you can find. So that's it for the somewhat boring syllabus details, and everything I just mentioned is on the course website, so the link is here. This is also on my courses, which again has a link to the website. And keeping things relatively simple, there's going to be a course website. That's where we have the schedule. That's where we'll put links to things. And then there's my courses, which is where we'll have announcements, where we'll do the quizzes, the grading, and have discussion board. So everything is going to be in these 2 places, and that's where you can look to keep up to date on what's happening in the course. All right, so now transitioning, yep. Yes, so there will be a PyTorch tutorial. You're welcome to do your projects in TensorFlow. I have a personal preference towards PyTorch, and there's a limited number of tutorials we can have. So yes, there will be a tutorial on PyTorch, which I believe one of them is on February 22nd and one on March 1st. If I remember, it's on the website, but off the top of my head, those are the deadlines. And there will be, one of the mini projects will also be an introduction to deep learning. So I know a lot of people are going to want to do their final projects on reproducing a paper that involves deep learning. So we will make sure that you learn that material in time for the final projects. Cool. So moving on to actual machine learning. So starting with a bit of a definition. This is a classic definition by Tom Mitchell, who's at Carnegie Mellon. So he says, how can we build computer systems that automatically improve with experience? And what are the fundamental laws that govern all learning processes? So it's a pretty vague, pretty high-level definition, and then down at the bottom, there's another more technical definition that basically just says machine learning is all about trying to build agents that can learn from experience to improve the way they act. So this is a pretty general definition, and throughout this course, really, we're just going to learn by example what machine learning is. And to that end, I'm going to start with actually just some case studies of machine learning today and what machine learning is doing, and in particular what applied machine learning is doing in the world. And these are going to be things that are going to take some time to build up to in terms of you being able to actually understand the methods behind how these techniques work. But they're going to be kind of some things to set our sights on for the semester. So the first big case study, and probably the biggest success story of machine learning over the last 15 years, really what started the deep learning revolution in machine learning, is the task of object recognition or object detection. So here the idea is that we want to feed an image to a machine learning algorithm and have this image identify or classify what the objects in this image are. So here we have an image of a cat, a TV, and the algorithm is automatically drawing these bounding boxes around these different objects. Now this is a slightly more complicated version. In the original versions of object recognition, we just had a simple image with one object in it, and you would just say, is this a cat or a dog? Now we can draw these bounding boxes, and in fact, just in the last year or so, we can get better than bounding boxes. We can actually draw the explicit outline, not just a box around the banana, but exactly detect the banana. So this task is seemingly simple, this idea of trying to detect objects in an image, but there's a really famous story where Marvin Minsky, who's one of the fathers of AI, back 30, 40 years ago, he had an undergraduate research assistant who he said, hey, I have this problem I've been thinking about trying to recognize objects in images, and he gave it to him as an undergraduate research project, so kind of like an USRA for people who've done those. And this is about 30 years ago, and they came back like, oh, it's kind of a little difficult. And so that was in the 70s, and it really took until, say, 5-10 years ago for us to actually solve this problem. And this is one of these big success stories based on what are called convolutional neural networks. We're going to go into this in a lot of detail. But the basic idea here is that we're applying filters to an image. So we're looking over patches of the image, applying some linear transformation to those patches, feeding that through some nonlinearities. So we apply functions that, say, take the max between a number and 0, things that are nonlinear. And then we feed this into what's called a fully connected neural network, and then we try to make this classification. Now this is all going to be maybe a little bit of gibberish. Maybe some of you are totally familiar with these kind of things, but we're going to learn all about exactly what convolutions are, what nonlinearities are, what max pooling is, etc. And this is important, this application is important because it's not just kind of a fun, look, now we can detect cats and dogs in images. There's actually been some really exciting and important applications of this just in the last few years. So for example, on the left, there's just a snapshot of this Nature paper. This is actually a good friend of mine who actually started a startup now based off this. And the idea was actually using these object recognition techniques, these computer vision techniques, to detect whether or not spots on your skin are cancerous or not. So they, in their paper, showed that they could be competitive with dermatologists, so actually trying to do this classification. And the idea is that you can think maybe sometime in the future of being able to get a diagnosis, maybe not a definitive diagnosis, but a diagnosis even just from your smartphone. And in related work, there's been a lot of fantastic work on looking at X-ray images, looking at fMRI images, and again, where the idea is that how can we complement the work that doctors are doing, that radiologists are doing? They look at thousands of X-rays in a week, some of them, and it's extremely time-consuming, so how can we build computer vision machine learning models that can complement what these doctors do and make their lives easier, as well as faster and reducing the cost of healthcare. And that's all well and good, but these methods are not without failures and not without controversy. So this is a very classic example. So here on the left, there's just an image of a face detector detecting a bunch of faces, but we've shown it on the right an image of some cookies, and you can see that it thinks that this one cookie in the second row is actually a face. This is a really traditional example, but this happens all the time, and false positives are funny in this example, but pretty major when you're talking about diagnosing cancer. And so there's been a really interesting back and forth over the past couple years between, say, doctors and practitioners and machine learning researchers about how can we have trust in these methods, how can we make sure that we're not sensationalizing results. And one thing that I want to make sure that happens throughout this course is that all of you gain the vocabulary, the background knowledge, so that when you see these big flashy news reports about the things that machine learning is doing, that you can look at those with a critical eye and understand what is the real development there, what are the risks, and why is it exciting, or maybe just a bit of hot air. So the other major application area of machine learning is natural language processing. So you have vision on one side and then language on the other. Of course, there's all kinds of other things, but these are really two big areas. And perhaps the biggest success story that you see day to day recently in machine translation in natural language processing is machine translation. So not everybody uses Google Translate. I actually use it quite a bit, but it's improved dramatically over the last 5 years, and it's done so, again, as a consequence of this deep learning revolution, so new techniques. So here I'm showing what's called this classic encoder-decoder, so what's called a recurrent neural network. So we have a neural network that's incrementally processing the sentences in English, and then it's generating the words on the other side in German. And I don't expect you to understand how this works now, but this is going to be, again, something that by the end of the semester, you'll actually be able to re-implement a model that does exactly this. And one of the core interesting principles behind this idea of translating between different languages, and really a core principle behind most of the modern successes of natural language processing, is this idea of representing words as vectors. So something you're going to see throughout this course is a really important thing in machine learning is not just developing better algorithms, but figuring out how to translate your data in the world into something that a computer can understand, some sort of ones and zeros, because you can't just feed in ASCII to some neural network model and expect it to work. You can't just feed in an image and expect a off-the-shelf classifier to work. You have to think hard about how are we representing these real-world objects in terms of ones and zeros in a way that our algorithm can understand. And one of the most successful ways of doing so is this idea of embedding objects, so representing things like words as points in some geometric space. So here I'm showing these very classic examples of these what are called embeddings of words, and what this is illustrating is that there's this really interesting phenomenon when we learn these kinds of models that say if we get the embeddings, the representation for king and queen, if we translate those, if we translate, say, the embedding for queen in order to get the embedding for woman, the same translation goes from king to man, and so on. So what happens is that when we learn these sorts of models, when we figure out the right way to encode these real-world objects into something that our computer can understand, this can actually start to reveal different kinds of structures and semantic information about the domains we're working with. Now, another area where machine learning has really impacted us, and where probably you don't think about as much, or maybe some of you do day to day, is the extent to which machine learning is involved in our day-to-day lives through recommendation engines. So I presume most of us use Google, most of us use Facebook, and all of these tools are learning from the things we do in order to make recommendations about what to show us, what news articles we should read, how Google ranks our page. And this is perhaps the most substantial, the most kind of in-your-face, day-to-day application of machine learning. You don't hear about it as much, but it's actually a really important and large application. And in terms of how this works, I won't go into detail here, but it's again this same idea where previously we were talking about taking words and how do we represent words as something a computer can understand. And now in this case, we're actually going to take not just words, but people and communities and things like news articles and try to embed these things, represent these things in some sort of low-dimensional vector so that our algorithm can make predictions. And we'll talk about these sorts of techniques around the last third of the semester. But something that'll come up earlier than that is ethics. So I mentioned this application not just because it's maybe something that we don't think about that much, but also because it's a really obvious application to bring up the fact that when we build machine learning models, we're building models, but we're also trying to build things that will hopefully be deployed in the real world, and that will have impacts on people's lives. So you might think that just recommending news is a pretty innocuous thing, but I think we can all know that these days, when we have these sorts of algorithms interacting with all the decisions we make throughout our day in apps, things like Facebook, things like Twitter, there are really important ethical implications in terms of the content we're seeing, the people we interact with, and so on. And I bring this up because even in the first mini project of this course, I'm going to ask you to build a little data set from some social media, actually from Reddit, for people who've used Reddit. But one of the things I want you to do when you're doing that is actually consider the ethical implications of the kind of task that you're developing, whether or not it's reasonable, what the expectations of privacy that people have when they're on these sorts of platforms. And this is not a course on ethics, but it's important that in all the machine learning that we do, that we have these sorts of ethical implications at the front of our mind, even things like object recognition. There is the use of these things for powering military technologies, for powering surveillance systems. So it's very rare that we have applications in machine learning that are devoid of any ethical implications. So that'll be a recurring theme throughout the course. So the very last case study I want to quickly mention is game playing. So we're not going to cover reinforcement learning in this course, which is the core technique that's used to power game playing agents. That's going to be in Comp 767, which is offered the same time as this. Recommend you take this course first. But in the last few years, for those of you who are interested in things like Go, which is a game similar to chess, there's been a lot of really amazing developments. And in particular, 5 or 6 years ago, when I took this course, the game Go, which is, again, it's a game similar to chess, but a bit more complicated. There's a much larger action space. And when I took this course, the Go was actually brought up as an example of something that AI couldn't do and that we didn't expect AI to solve anytime soon. So it was an explicit example used to highlight, how even game playing, which is this very classic AI domain where our machines have been better than humans at chess for a long time. But in the last few years, not only have artificial intelligence agents won at Go, but actually just a few months ago, an agent called AlphaGo Zero, this is by Google DeepMind, learned totally from scratch. So it didn't know any of the rules. All it did was played games against itself for 40 days, and it got to Grandmaster level. Not just Grandmaster level, but actually currently the best Go playing system out there. So it's pretty interesting, pretty exciting. And how this system works is, again, unsurprisingly, based on deep neural networks, where we have one network that's taking in the board state and trying to figure out, is this a good board? Say I took this move, would that be a good idea? So here on the right, demonstrating these rollouts, so trying to figure out all the different possibilities of what could happen. And unsurprisingly, again, based on these recent deep neural network methods, and this Go success, especially this agent called AlphaGo Zero, generated quite a bit of attention. A lot of people, being maybe sensational about the ability of this technique. So an interesting one, which I actually recommend to read, again, to take with a grain of salt. This is an essay from the New York Times a few weeks ago. This was called One Giant Step for a Chess-Playing Machine. It's by Steven Strogatz. who's a really amazing researcher, actually mainly in network science. But he has this one quote where he says, "Most unnerving was that AlphaZero seemed to express insight. It played like no computer ever has, intuitively and beautifully, with a romantic attacking style. It played gambits and took risks." So this was quite a sensational description of a artificial intelligence agent. And in fact, people who are really into Go, I don't play Go, but they said it really did have an extremely interesting and kind of sophisticated playing style. And this generated a lot of controversy, showing here one tweet by a prominent ML researcher who I won't name, but who actually contacted Stephen kind of trying to say, hey, this is a bit sensational. You're going to make people worried about AI taking over the world. I'm not particularly worried about AI taking over the world, but I mention this example just because game playing and these sorts of artificially intelligent agents that play StarCraft or Go, they're often highlighted as kind of the pinnacle of machine learning and applied machine learning. And we're actually not really going to talk about this. For one, again, because the technical methods are covered in a different course, but also because these are applied in that they're playing games, but they're not really a real-world application. This is kind of the last sandbox where people are playing around with interesting AI techniques. But I highly recommend, if this really inspires you, take 424 and also take Comp 767, and you'll learn all about the fundamentals of how this algorithm actually works. So this is a really good question. So the question was, it says in this quote that AlphaGo is taking risks, and so does this mean that it was playing suboptimally and just happened to win, or did it have some grand scheme? And this actually brings up a really important point that I wanted to mention, which is we don't know exactly, which is I think why there's been a lot of maybe sensationalism surrounding this, is because with the rise of these techniques around deep learning, we've gained a ton of performance, and in this case, AlphaGo is able to play these really intricate games where it looks like it's doing something crazy and then it wins in the end, but we have no way to unpack why it's making those decisions. And that's one of the major pitfalls of the deep learning methods, again, what'll be kind of the latter part of this course, is that unlike the methods we're going to cover in the first half of the course, which you can really understand for the most part exactly how they work. We know why they're making decisions. It's kind of baked into the way the model's designed. With these more recent and arguably much higher performing methods, there's no way to unpack the decision making. And so we think that it's taking these risks not just because it's being silly, but because it actually has a grand scheme, because it never actually lost a game against the next best system. It only took draws. But we have no way of knowing why. And interpretability is a theme that will also recur and also be tied in with ethics that I mentioned just a few slides ago. All right, so that was a really quick tour of what machine learning is doing today. Hopefully you're sufficiently inspired and at least interested in one or two of these applications. Again, we're not going to start next lecture talking about how AlphaGo Zero works. We're going to start with the fundamentals, but by the end of this semester, you will have the tools to understand the vast majority of all these applications I just discussed. And concretely, what are the kinds of machine learning that we're going to cover? So now I'm going to transition and just talk quite briefly about the high-level kind of taxonomy of machine learning, what we're going to cover, some of the key terminology, language, vocabulary, and then we'll close out the lecture a bit early. So in terms of machine learning, the key taxonomy here is we have techniques that are called supervised learning. I'll explain what that is. That's basically where we show the agent examples of, here's a cat, here's a dog. Now be able to generalize and detect more cats and dogs. There's what's called unsupervised learning. That's where we just give a machine learning algorithm a big data set and we say figure out something interesting. Maybe detect some anomalies, maybe cluster the data. And then the other big branch of machine learning is what's called reinforcement learning. And this is where we're actually letting an agent go in some environment, having it learn from delayed feedback and optimize some sort of policy for how it should act over time. And like I said, reinforcement learning is an extremely interesting area, but because there is a concurrent course, a special topics course exactly on this, we're really not going to cover much reinforcement learning at all. Though I will say that the things you will learn in this course are prerequisites for being able to understand modern machine learning. So it's not like this has nothing to do with it. It's just reinforcement learning is in some sense maybe the more advanced of these three branches within machine learning. And in terms of the language of machine learning, so terms that you're really going to need to remember because I'll use them all the time from here on out. So the classic thing in machine learning is we have some data set. So here at the bottom of this slide, this is an Tory data set where we pretend that, say, we are trying to predict tumor recurrence, so whether or not a tumor was going to recur, and we're trying to predict also maybe the size change in this tumor over, say, a 6-month period. So we have a bunch of columns here. These are the input variables. They're also called features or attributes. I'll usually call them features. And what these are is this is the information we're giving the algorithm so that it can try to make the prediction about the output variables or the targets. So for example here, tumor size, texture, perimeter, shade, this is all information about some particular tumor. These are the input variables or the features that we might try to use to predict whether or not, say, this tumor is going to reoccur. That's what we call the targets. And a row in this table we'll call a training example or an instance. So one example tumor, that's usually called a training example, sometimes an instance, and the whole thing is quite simply a data set. And this is the basic sort of system we're going to be working with, especially for the first half of this course, really talking about what are the features, what are the targets, how are we going to slice and dice the data set in order to make predictions. Now I mentioned supervised classification, so just a bit more concrete detail on what that is. Or supervised learning is sometimes called, where classification is a particular style of supervised learning. So here the goal is to take some features, some input variables, and then make a prediction about some categorical output. So we're not trying to predict a real number, we're trying to predict a category or a yes or no. So a really classic example of this is spam detection. So we get in some emails, a bunch of feature information about those emails. Is there certain phrases? Is things in all capitals? What sorts of punctuation is there? And we're trying to predict whether or not this is spam or not spam. So that's supervised learning, the classification version of supervised learning. Now the other version of supervised learning that is most standard is what's called regression. The name regression is somewhat of a historical oddity, but here what this means is that we're again taking some input features, but instead of trying to predict a category or a yes or no label, we're trying to predict a real number. So an example for, in this case, would be, say we want to predict or determine what the output speed should be for a self-driving car. There we're taking in a bunch of input information, a bunch of sensors, a bunch of visual information, and our target is to predict what is the output speed. And this is a continuous variable, so we call this regression. And this is what we're going to start the course with in the next lecture, is supervised learning for regression using a linear model, which is the most basic but probably the most important machine learning model you'll ever learn about. So besides supervised learning, as I mentioned, there's this idea of unsupervised learning. So one of the most common versions of unsupervised learning is we're given just a bunch of data, just a bunch of examples where we have some feature information, and what we're trying to do is just organize this data in some way. And clustering, what we mean is we're trying to cluster this data into some meaningful groups. So in the bottom left is an example of how we might cluster this set of points into a bunch of different spatial clusters where they're colored differently. On the right, I'm showing a hierarchical clustering where we infer some sort of taxonomy. But again, the basic idea is that I say give you a whole bunch of students, and you want to cluster them so there's some meaningful information, and at the end you say, oh look, these are all students who share these sets of interests, etc. So it's more for data discovery, whereas supervised learning is solving some particular application task. And then finally, another version of unsupervised learning is what's called generation. And this is a more advanced topic. This will be right towards the end of the semester. But here, we're not just trying to cluster or organize the data in some way. Here, the idea is that I want to show a machine learning algorithm a whole bunch of examples of some data, and then it's going to actually generate examples that could come from that same distribution. So at the bottom here, this might not look that impressive because it's just a picture of a dog, and a picture of a butterfly, and a picture of a burger, and some landscape. But these are actually fully artificially generated images. This dog does not exist in the real world. A deep learning algorithm, this was actually published a few weeks ago, so it's a very recent method. It's the state of the art right now. But it's quite impressive that you can't tell too much in this poor resolution, but these are extremely high resolution images. And this dog has all the features of a dog, but it's completely made up. And I'm not showing some of the crazier ones, because you can also do things where you ask the algorithm to have one image of, say, a dog morph into an image of a person. It can learn to interpolate between these things. And right now, these techniques are largely being used in vision. They have some nefarious applications related to making fake videos and things like that. But in the next few years, this idea of learning to generate realistic data is going to be one of the really big application areas in ML as it moves beyond just vision. And then finally, the last thing I'll talk about today is just these 3 open challenges. So I talked about the structure of the course. I talked about some exciting case studies, how machine learning is doing well, maybe some of the potential pitfalls of current machine learning, and then also this taxonomy and these vocabulary that we're going to use to talk about machine learning. But of course, I shouldn't say that machine learning is far from a solved problem. There's definitely a ton of open challenges left. And at the end of this course, you should not just know a lot about kind of what the current state of the art is in machine learning, but you should have the skills, the techniques to actually try to kind of push things forward. And where are the broad areas where, in my opinion, things need to be pushed forward? Well, for one, there is efficiency. So I talked about Google Translate, this machine translation. This is really exciting. We have this really amazing translation engine. But that takes hundreds and thousands of GPUs. That warms up the earth to do that. So I'm actually not kidding. It does actually warm up the earth. So it's actually a big deal, for one, because it's really expensive. It's kind of a waste. But also because it's extremely power intensive. And deep learning works really well. But right now, a lot of the successes rely on a ton of data and an absolute enormous amount of compute power. So building more efficient models is really important because, obviously, a human person who is an expert at translation doesn't warm the earth up just by thinking really hard. So this is an important thing and something to keep in mind as we're going throughout this course. Another really big theme in terms of open challenges is generalization. So I mentioned this really amazing AlphaGo Zero algorithm that it learned to just play against itself and became the best Go player in the world. This was something that 6 years ago we thought was kind of out of the question. This is really impressive, but what's not impressive is how brittle these sorts of algorithms are. So we can't take this Go playing algorithm and have it play a different version of Go. We can't have it play chess. We can't have it solve a maze. All it can do is play Go. And this is a really big fundamental challenge right now in machine learning. Probably the biggest challenge, in my opinion, is how can we actually build algorithms that are capable of real generalization? And I'll talk about statistical generalization as a concept in a few lectures, but this is more than that. Because when humans learn, humans don't just learn what a cat is and what a dog is and end of story. Humans learn to be able to figure out all kinds of animals and learn from single examples. And this is a really big challenge over the next maybe 10, 15 years, is actually building AI agents, machine learning models that can truly generalize. And then the last example, something I've already talked about a bit, but I'll reiterate, is ethics. I think as machine learning is getting more and more popular, it's going to be more and more important that we don't just think about what is the fun, crazy model, but also what are the implications of the deployment of this model. And this will be something that recurs again throughout the course. It's a good question. So the question is just, I mentioned how expensive a lot of these models are, and the question is, how is that the case if we can have translation happening on our phone? Is that because we're actually sending information off to some server where the computation is actually being done? One of the most important things is the distinction between training a model and deploying a model. So the really big expensive thing is training the model, is teaching the model how to do translation. Once it's already built, deploying it isn't actually so bad. And there's an active research area in machine learning called model distillation, where the idea is we train a really big, crazy model. That's crazy expensive. And then afterwards, we figure out how to compress that model. And once we've compressed it, we can put it on embedded devices and so on. This is a good point, and this is this important distinction between what we call train time versus test time. And I will say that at this point, I am finished the main content of the lecture. I'm happy to answer any questions that people have, but also if you want to get going, maybe it's ad drop period and you want to try out a bunch of courses and have places to be, feel free to head out. So thanks. And feel free to just come up here if you have questions.